of aldehyde and ketone by reduction. Okay. Reduction actually, you can either use catalytic hydrogenation reaction, nickel, platinum, palladium, and all, right? And that is going to make hydrogen get added to the double bond, right? So that is very simple, H2PT, out of which H2Na is very reactive. Nickel is the most reactive one. So you are going to reduce the double bond O and you will end up with an alcohol, right? So yeah, so NaBH4 or there are two types of reducing agent. So one is catalytic hydrogenation reaction. Okay. So in catalytic hydrogenation, what we are doing, we are actually taking the catalyst and we are adding the hydrogen. Okay, the double bond get absorbed on the surface of the uh, catalyst. Hydrogen get absorbed on the surface of the catalyst, right? And the hydrogen get added to the double bond. Okay. So what type of alcohols can you prepare? Just a simple question, but a very important question. What type of alcohols can you prepare by catalytic hydrogenation reaction? Primary alcohol, tertiary alcohol, secondary alcohol. Which type of alcohol can be prepared or which cannot be prepared?
Tertiary cannot be prepared.
Yeah, tertiary cannot be prepared because there is no hydrogen, right? By catalytic hydrogenation reaction and non-aldehyde and ketone. So you can't prepare tertiary. Aldehyde ketone have to only two alkyl groups. So if you have only two alkyl groups, actually, and if you put HH, you are going to get only either you are going to get primary alcohols or secondary alcohol. Tertiary alcohol can't be prepared, right? Correct. And there are other set of reagents, and these other set of reagents are known as hydride donors. Okay. So what set of reagent come in this category? Yeah.
Sir, hydrate don't means donated hydrogen.
H minus donors. Actually, ALH3 is neutral. Okay. And if you have one extra H minus, that will get added to aluminum vacant orbital, and that will, so whole thing will become ALH4 minus, Li plus and ALH4 minus. Similarly, you have that Na plus and BH4 minus, right? Okay, these are hydrogen. And which one is stronger? Reducing agent. Yeah. Yes, Amara, tell me, which one is stronger reducing agent? LH is stronger. And what is the name of LH? Complete name for LH? It is lithium aluminum hydride. and this is SBH, sodium borohydride, right?
Yes, sir.
So which one is stronger reducing agent? Any idea?
Maybe lithium aluminum hydride.
Which one?
Lithium aluminum hydride.
Yeah, that is stronger reducing agent because H can come out, break away more easily. So it is stronger than NaBH4. Okay. So sodium borohydride will reduce only aldehydes and ketones, right? But carboxylic acid, esters, amides, carbon-carbon double bonds, carbon-carbon triple bonds, they will not be reduced by NaBH4. On the other hand, LiLH4 you can take. LiLH4 can reduce aldehyde, ketone, carboxylic acid, esters, acid chlorides. So all are going to give you alcohol, okay, except amides. Amides will be reduced, but with LH you are going to get amines. So that comes under the preparation of amines. But double bond and triple bond still can't be reduced by LiLH4. Is it clear?
Yes, sir.
So if you want to do the selective reduction of aldehyde and ketone, you better choose an NaBH4. Okay, and NaBH4 is not a very strong reagent, and you can use ethanol also. You can use Protex solvent also. You can use it with water, methanol, ethanol. But LH you can't use because other this H minus will react very quickly with the water. Okay, so yeah, this is the thing which you can see over here. So LH is there, carboxylic acid is reduced. Look here, they are not reduced. Okay, so this is how we can do. So I hope this is clear. So let's do this. So what you are going to get? Yes, Amara. LH upon reduction of esters. Okay. So what's the mechanism? So this is the addition of H minus, nucleophilic addition of H minus. Actually, double bond O will form again, and it will push away this OR group, alcohol group. So you will end up with, right, this one and R dash OH. Actually, this will attack, this is an aldehyde. So it will be attacked again by LiLH. And finally, you will end up with RCH. So you are going to get two alcohols. Okay. Is it clear? But if you take,
Yes.
if you would have taken NaBH4, the reaction may not have occurred because NaBH4 will reduce aldehyde and ketones only. Okay. So let me suppose this is cyclohexanol, right? So what will be the products for these?
So what is that D2O?
D2O is actually deuterium. This is deuterium. This one. Okay. The heavier isotope of hydrogen. Okay. So it is written as D. And this is heavy water, right? This is there in the hydrogen chapter of class 11th. So actually, so this is H and this is deuterium. So where the question is where you are going to put H and where you are going to put deuterium. Okay. So the thing is, it's very simple. This carbon is plus and this oxygen is minus, right?
Yes, sir.
So what happens is, and this is H minus, right? And the deuterium with water. So whosoever is in the water, either it is D plus or H plus. So that will be the plus form. It will be D plus. And whatever the isotope is there with the aluminum, that will be minus. So this minus is going to come and attack over here. The double bond will get shifted by the nucleophilic addition. O minus is going to form. And this D is going to go and add on that oxygen O minus. Is it clear? So initially you will have O minus forms. Normally what happens is sometimes we ignore, we just write LiLH put. If nothing is mentioned, you can just put OH, that's it. But if somebody deliberately asks you LiLH4 and D2, then you need to be very careful. Okay, so where to put H, where to put D. So H minus will come at the carbon. H minus from LH is going to come and join itself to the carbon because carbon is partially positive. O minus is going to form and O minus will react to D plus. Okay. So OD will form, right? And in the lower case, it is going to be the reverse. Here the D will get connected to the carbon and that will be OH, right? Clear?
Sir, I don't understand that. Oh, that OD and the.
So D, what is D? Is it clear? Is this
No,
clear?
sir.
This is hydrogen only, but the heavier isotope of hydrogen. This is heavy water. What's the molar mass of water? Tell me. It's 2 plus
18.
18 U, right? So what's the molar mass of heavy water? This is known as heavy water.
So that I don't know.
Yeah, you can calculate very easily. This is deuterium. So it is having, so normal hydrogen is having one proton and one electron, right? Deuterium
Yes.
is actually the heavier isotope. It's the isotope of hydrogen only. One proton, one neutron, and one electron. Electron mass we don't consider. We consider only the mass of proton and neutrons. So its mass is twice. Its mass is one due to one proton, and its mass is going to be twice. Right?
Yes, sir.
So actually, this is known as isotopic labeling technique in order to understand the mechanism in detail. So which hydrogen is getting added from the aluminum? Aluminum, whatever hydrogen, aluminum is a metal, so whatever the hydrogen is there with the aluminum, that is H minus. And whatever the hydrogen which is there with the in the form of water or D2O, that is D plus. And in order to make these differentiate these hydrogens from one another, what I did, I took one as hydrogen and one another as deuterium. So this H minus is going to come over here. O minus is going to form O minus Li plus. Now after once you do the neutralization with water, D plus is going to come and add over. This is the case. Understood? So a lot of questions also come. Okay, so just a little bit. So here D minus will come out from the LH, and that is going to go and attack on the carbon D minus. Okay, and O minus will form, and H plus from the water. Water will give H plus, and this is the normal isotope of that. So OH and D. So this is going to be the answer for the second case. Okay, and this one here it is going to be H and O. This is going to be the answer for the first case. Is it clear?
Yes, sir.
Okay. So yeah. So esters and all, we know esters are going to get cleaved by LiLH4, but NaBH4 is not going to cleave the esters. Okay, aldehydes are going to change to primary alcohol, ketones are going to change to secondary alcohol. Okay, that's that what we did. So this one, tell me what's going to be the answer to this one. Yes, Sumaira. So what you are going to get? So what is going on in your CBSE batch? Tell.
Sir, in Learnivio,
Yeah.
right now, electrochemistry.
Okay. And you have covered that aldehyde ketone carboxylic acid.
No, sir. I shifted my batch. I wanted to study electrochemistry for that.
Okay, 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 okay. So CH3Br and KCN. So this is alkyl aryl halide. Okay, this is clear. What is A?
Yes, sir.
CH3 CN. Okay, and now what will happen if you hydrolyze CN? A small trick I am going to tell you, that 3 double bonds. So you can put 3H and 3OH. Is it clear? This is a quick trick.
Yes, sir.
So CH3, C, OH, OH, OH. But two or more than two OH are unstable. So what happens here is the water is going to get eliminated, right? And the water is going to get eliminated, and you are going to get a carboxylic acid. Okay, clear?
Yes, sir.
So now LH and ether, LH is going to reduce that carboxylic acid to alcohol. So what is going to be the answer? Ethyl alcohol. Okay, right?
Yes, sir.
So this preparation of phenol that you know already, okay, by benzene. So first we need to put the chlorobenzene, and then we need to heat it with NaOH strongly. So that is bimolecular NAS, right? That we did in that nucleophilic aromatic substitution also.
Yes, sir.
So this thing I can skip. So just if you have any doubt, I can explain you, not a problem. We discussed that if you have NO2 groups at ortho and para position, so they are going to bring the plus charge, right?
Yes, sir.
Because of the resonance. So the attack is going to become more and more easier. So you can notice that by lowering of temperature. And if you have three NO2 group, just you need to take water and warm it, you will get picric acid. Okay. And this is another method by sulfonic acid sulfonation. You can do the sulfonation and NaOH heat. You're going to get phenol. Okay, this is also bimolecular NAS. Okay. So next is preparation of phenol using diazonium salt, right? So just quickly, from benzene, how can you prepare by diazonium? Yeah. How can you prepare by diazonium? Any idea? From benzene. So benzene, you can do the nitration. Okay. You can reduce the NO2 group to NH2 by taking 10 NHCl, react it with NaNO2 plus HCl. You are going to get a diazonium salt, heat it with water or dilute H2SO4. That is going to substitute the N2 plus group by OH group, and you will end up with a phenol. Okay. And this is cumene hydroperoxide method. So how do you prepare cumene? This we did earlier also, or it need to be covered.
So we didn't do, I think. Didn't do.
Okay. Yeah. So what is the other name for cumene? Can you tell me if you remember?
Isopropyl.
Yeah, isopropyl. And how can you prepare it? So sometimes it is given from cumene, and sometimes they give from benzene itself. So from benzene, how can you get the isopropyl benzene? You can either take propene, CH2, NH plus as a catalyst. So H plus is going to come and join to the CH2 plus, and you are going to get CH3, CH plus, CH2, CH3. And this cation is going to go and join itself to the benzene ring. So you are going to end up with a cumene. Okay.
Okay, sir.
Or there is another method also. You can take isopropyl chloride and AnCl. That is also Friedel-Crafts alkylation. Cumene, you treat it with what? Tell me. You treat it with oxygen in the presence of heat and light. So actually, this hydrogen is very reactive. Okay. So this hydrogen will be abstracted, benzylic hydrogen. And you will have OOH connected. Okay, this is cumene hydroperoxide. And what you take in the last step? Just try to recall quickly. Yes, Samaya. Yeah. You take conc H2SO4. So this H plus is going to come and join to this OH, and the water will get removed. A cation is going to come on the oxygen, and the benzene is going to get shifted on the oxygen plus in order to make a cation more stable. Is it clear?
Yes, sir.
So you will have C plus O and pH. And because it is aqueous medium, so ultimately you will have OH connected on this. So on one carbon you have OH. The pH got shifted to the adjacent oxygen because of the removal of the OH group as water. And this whole thing again breaks into phenol and acetone. Okay, acetone, this is acetone. The left portion and the right portion is phenol. So many questions are asked on the byproduct. So these, they come in all the examination, very common, very important. So yeah, tell me. What's going to be the answer to this one?
So
Yes, Amaya.
option
Yeah, option.
C.
Option C. Yeah, exactly. So this is the cumene hydroperoxide, which upon treatment with H plus, it undergoes rearrangement and then you get the phenol and this. So this is correct. And what about this one?
So is it A?
What you are thinking is partially correct. Actually, you always need to keep one thing in mind wherever there is a formation of a carbocation. Okay, if the carbocation can move on to the adjacent position and become more stable, then it will become more stable. Then it will undergo rearrangement, right?
Yes, sir.
By shifting onto the adjacent position. So here the immediate position the cation formed will be normal profile cation, and this is primary. Okay, and it is going to come over here. Why?
Because it will be second. It will form secondary.
Yeah, it will form
More
secondary.
stable.
Yeah, more stable. Right, and once it has stabilized itself, and then that we are going to take the final decision about the fate of the carbocation. So ultimately it is given with benzene, so now we are going to put on the benzene. So we are going to get the cumene again, right?
Yes, sir.
So A is going to be cumene, and that is there in the option C and D. Now tell me, what is going to be the answer?
So option D.
Option D, right? Because here you have acetone. That also you need to keep in mind. Many question in JEE also they ask this, because most of the people they forget, because the whole focus is on the phenol, so they forget what was the side product. That is acetone, right?
Yes.
Okay, acidic and basic strength actually, which alcohol is more acidic and why? How the acidic strength changes with branching of the alcohol? Yeah,
So, sir, if more branching is there, it will be more acidic.
it will be less acidic,
Less.
because suppose if you are removing H plus, so whatever you get after the removal of H plus, whatever is left behind, what that is known as? That is known as conjugate base. So an alcohol is going to be acidic if it is conjugate base is stable, right? And
Yes.
what makes the conjugate base stable? What makes the conjugate base stable? The less and less branching. Suppose if you have more and more branching, this is the inductive effect, plus I effect. Because alkyl groups are less electronegative, so they are considered to be electron donating groups. So if you have more and more electron donating groups, what will happen to O minus? The O minus is going to become less and less stable. It is going to become more and more negative, right?
Yes, sir.
And it is going to become more and more negative. So you are not promoting the departure of H plus. If it becomes more negative, what it will happen? It will again call it H plus. Okay, come back and join again. Okay, is it clear?
Yes, sir.
So you need to have smaller and smaller alkyl group to make the alcohol more and more acidic. Okay. So water, look at the larger the alkyl group you have, the less and less acidic your alcohol is going to become. And less acidic means what? Less acidic means what?
More branching.
More branching. Yeah, more branching. Right? So less and less acidic it is going to become, right? pK is going to increase. pK is going to increase. Is it clear?
Yes, sir.
So acetic acid is more acidic, okay, and HCl is going to be much more acidic, okay, clear. So what about the phenol? Phenol and cyclohexanol, which is more acidic? Tell me.
So phenols.
Why? Phenol pK is 10. You can remember this. Rounded off to 10. Okay.
Okay, sir.
So it is more acidic than water, definitely, and normal alcohol. Why? What's the reason? So you need to think of wherever you have acidic strength, don't try to think on the molecule itself. First, remove the H plus. After the removal of H plus, whatever the conjugate base which you get, think whether it has stabilized itself. If it has stabilized itself, it will not bring back the H plus. And if it has not stabilized itself, then it will bring back the H plus and it will go and join again with the H plus. So in the case of phenol, this is phenoxide ion, and the phenoxide ion actually after the removal of H plus, the phenoxide ion forms, and the phenoxide ion is stabilized by resonance. You can see this negative charge get dispersed at so many positions. So it's good for the minus because its electron density is going to come down, and it will become more stable, right?
Yes, sir.
Okay. So, and presence of NO2 group is going to make the conjugate base phenoxide ion much more stable. Okay, but you need to be very careful about the position of the NO2 group, where it is placed with respect to the OH. So where it should be, that will help the phenoxide ion to become more stable. Yeah,
Para position.
the para and ortho position,
Okay.
because the phenoxide ion negative charge, when it gets into the ring, it passes from ortho and para position. And if the NO2 is there, like in the lower case, look here, this minus charge can get onto the NO2 also, so it will get more places to get delocalized spread, and it will become more stable. But if the NO2 is at the meta position, then it will not help much because the minus charge is not passing from the meta position. So ortho and para nitro groups or electron withdrawing groups at the ortho and para positions of the phenol will make it more acidic. Is it clear?
Yes, sir.
So what's going to be the acidic strength of orthonitrophenol, metanitrophenol, and paranitrophenol? This was a question I have not put here actually, but it was given in reason or session in NEET. Okay. So what's the increasing order of acidic strength?
So the para-nitrophenol is the most acidic,
Yeah,
and this meta-nitrophenol is the least.
yeah. So this is the order of acidic strength. But why para is most acidic? Actually, the ortho should be expected to be more acidic. Why? Because the ortho NO2 is an electron withdrawing group, and being close to OH, it is going to withdraw more easily. Yeah. Actually, what happens here is there is one more thing. Actually, this orthonitrophenol, the OH finds itself locked in intramolecular hydrogen bonding. Are you getting what I'm trying to say?
Yes, sir.
So actually, it is locked. It is getting attracted by O minus of NO2. So it becomes difficult for this H plus to come out. But in the para-nitrophenol, that is not going to happen because NO2 and OH are far apart. So that's why this ortho is a bit less acidic than para. Okay, though we expected it to be more acidic, but due to intramolecular hydrogen bonding, it actually acidic strength decreases. Clear?
Yes, sir.
And yeah. Now the next thing is, what's the boiling point of orthonitrophenol and paranitrophenol? That again is a very common question. Yeah.
So maybe the boiling point of orthonitrophenol is higher.
Is higher or lower?
But I actually don't remember.
Yeah, actually what happens is the orthonitrophenol molecules, they don't interact with one another. Actually, they are actually cocooned within themselves only because they are forming intramolecular hydrogen bonding. Is it clear? Intra means within the molecule.
Yes, sir.
So they actually cocooned within themselves only. So they don't, they are not connected to their neighbors. But that thing can't happen in paranitrophenol. Paranitrophenol, actually the OH and the NO2, they are far apart, and they also participate and attract the H plus, okay, one another. So but they can't attract their own group because they are opposite. So they get associated with other nitrophenol molecules. So in a way, all the molecules are associated to one another. Is it clear?
Yes, sir.
And that is the reason and suppose if all the molecules are associated to one another, then what is going to happen? You need to put in more heat to make them to boil them, right? Is it clear?
Sir, can you please repeat?
Actually, suppose if all the molecules are joined to one another, okay, and if you want to boil them, will it be easier or will it be difficult for us to boil?
Difficult.
Yeah, difficult, because you need to break their associations. So you need to put in more heat. So the boiling point is higher for para-nitrophenol. Is it clear?
Yes, sir. Clear.
And there is a very, very common question. How do you separate orthonitrophenol and para-nitrophenol?
By steam distillation.
Yeah, steam. And why the steam distillation? Which isomer is distilled by the steam?
Sorry, what, sir? What did you say, sir?
Which isomer is steam volatile? Is it the orthonitrophenol or the para-nitrophenol? Which can come out easily with the steam?
The orthonitrophenol.
Yeah, orthonitrophenol is steam volatile. It is because the molecules are not getting associated to one another. They come out very easily. Para-nitrophenol require higher temperature to break their bonds. Is it clear?
Yes, sir.
Yeah, okay. So this is the thing, very, very important. And if you would have taken concentrated HNO3, you will get picric acid. Clear?
Yes, sir.
So normally for nitration, you take mixed acid. Okay, a mixture of two acids. Okay, but in this case, you will take only, because phenol is already activated, so you don't require concentrated H2S4. Just simply dilute HNO3 will work. Right?
Yes, sir.
That will be sufficient. Okay. So in halogenation also, in normal benzene we take Lewis acid catalyst like Br2FeBr3, Cl2, AlCl3. But in this case, in the phenol, you don't want to take those Lewis acid catalyst because the phenol is already highly activated. Just now we have seen the resonance structures of phenol. It has negative charge, and this negative charge itself on its own is powerful enough to push away the Br minus from Br2 and the Br will get attached. Is it clear?
Yes, sir.
But can you tell me the reason why if you take Br2 in carbon disulfide, you get only one Br connected either at ortho and para, and if you take Br2 in CCl4, Br2 in water, bromine water, 3 Br get connected. And this is also a test for phenol. This is white PPT. Right? What's the reason?
Sir, I don't remember.
Yeah, but do you remember this? This is how actually it happens. This is very
Yes,
important.
this I
Yeah.
remember. I don't know the reason.
Yeah, reason is in water is a polar solvent, so phenol get ionized to phenoxide and H plus. Reason is very simple, and phenoxide being O minus present on the phenoxide, it is more electron rich, so it's going to be more reactive, and directly you will have the Br groups connected at all the positions, right?
Yes, sir.
But in carbon disulfide, that is a non-polar solvent, so this doesn't get ionized. This will not ionize, and the OH will not become very reactive. Okay. Clear?
So can you tell that so that I can note it down?
Yeah. So carbon disulfide. So pH will remain unionized. Is it clear?
Yes, sir.
So Hanifa, you are also there. Sorry, I didn't notice. So can you hear my voice?
Yes, sir.
Yeah, you can also tell me your doubts. Actually, I thought that only Sumaira is there. So sorry about that. Yeah. So just I was discussing about the phenol. Okay. Right. And this I hope is clear. So this is also a test for the phenol. Okay. Now the next very important reaction of phenol is Riemann reaction. So Hanifa and Samaira, can you tell me what this is about? What this reaction is about? Riemann. What is the reagent? What we take? What we get? Yeah, quickly tell me. Hanifa and Samaira. So what's the intermediate in this? Apart from the one which is shown here. Yeah, Samaira, Hanifa, can you tell me quickly? Riemann reaction is actually formulation of benzene ring. You get CHO attached on the phenol, formulation of phenol at the ortho position. Okay. So mechanism is clear, or do I need to discuss it? Samaira and Hanifa, tell me quickly. And or we can
Sir,
directly, yeah. Tell me.
clear, so I say.
Yeah,
Mechanical.
okay. Yeah, okay. We can discuss some questions. This is the latest question, not very old. 2018 question. So what's going to be the answer, Hanifa? Yeah.
I'm not sure, sir.
Okay. So, Samaira, what's the answer? Any idea? Actually, there are a lot of intermediates. So the first one is because you are taking NaOH, so the phenol will change itself to the phenoxide ion. Okay. The phenoxide ion is resonance stabilized, so it is having minus charge at the ortho and para positions, right? But we are going to put the CHO on the ortho position because there are two ortho positions. Okay. So now the next thing is, what happened to this chloroform and NaOH? Yes, Amira. Hanifa, this chloroform has acidic hydrogen. Okay. The H plus, there's a H plus will be abstracted by the base OH minus. So first you end up with a carbon ion. Okay. Then the what H plus is abstracted by the base. Then Cl minus is a good leaving group. It comes out, it breaks away from this. So what you get? You get something. So there is already a minus charge, and if Cl minus comes out, there should be a plus charge, right? But actually plus charge doesn't come because the minus which is present already at the position get neutralized by the plus, and you have the neutral species. But this neutral doesn't mean it is stable. It is highly unstable. It has 6 electrons. And it is an electrophile, and that is known as dichlorocarbene. That is the intermediate. Okay. It goes and join itself to the ortho position of the phenol. Is it clear?
Yes, sir.
So, and that's how the reaction starts. So you end up with this and this and such. And then we proceed in this one. Okay. So what's going to be the answer to this one?
Option D.
Option D, yeah, dichlorocarbon. So there are quite a few reactions in organic which have dichlorocarbene as intermediate. And the another one is isocyanate test. Okay, in amines of isocyanate test and of primary amines. Okay. So now let's do this. So this is another reaction which is known as which is studied along with remetimin, but quite a different reaction. But the products are very similar. The names are similar, but the functional groups are different. There you end up with salicylaldehyde, and this one is your salicylic acid. Okay, clear?
Yes, sir.
And so this is always reaction. You heat phenol with NaOH and CO2, and that you end up with this. So this mechanism is quite easy, very easy. The phenoxide ion, you have minus charge on the ortho position. Hanifa, and CO2 is the electrophile. It has a plus charge on the carbon, right? This minus is going to come and add over here, and this pi bond will get pushed out away, and so you will end up with CO minus and COH, and ultimately you will get the salicylic acid. Okay, that's how it occurs. So can you tell me any other set of reagents apart from CO2 and NaOH which also convert the phenol to salicylic acid? Any other set of reagents? Yeah, tell me. Yeah, any idea? Hanifa, and so what should I write? Other set of reagent which converts, and it's there in your CBSE book also. Yeah, the reaction looks very similar to remitimine, but it's not remitimine. The reagent also look very similar to what we have used in remitimine. Samaira and Hanifa, tell me quickly. Yeah. Any idea? Hanifa and Samaira, the reagent is NaOH and along with CCl4. Is it clear?
Yes, sir.
Okay. So that also is very important. Okay. So if you take chloroform, you will end up with aldehyde group. But if you take CCl4, you will end up with carboxylic acid group. If you take COH, okay, if you take CO2, then also you will end up with carboxylic acid group. Is it clear?
Yes, sir.
Right? Okay. Good. So do remember this, as there are two methods, and this is pull-based reaction. Okay. So that was formylation of phenol and carboxylation of phenol, and this is the reduction and oxidation of phenol. Reduction, if you heat the phenol with zinc dust, just one reaction, but very, very important. It is there in your NCERT also. It will remove the oxygen and you will end up with zinc oxide and benzene. And if you take any oxidizing agent, strong oxidizing agent, you're going to end up with two double bond. Okay. Is it clear?
Yes, sir.
So let's do this question. So what's going to be the answer? Yes, sir. Hanifa, what's the answer?
So I think B.
B, benzoic acid. Yeah. So phenol, zinc dust you are taking, that is going to give you benzene. Hanifa, do ask me if you have any doubt. This is AlCl3 is going to take away the Cl minus and you're going to end up with CH3 plus, which is going to come and join itself to the benzene ring, and you will have toluene. And any chain, if you take and if you oxidize it, it oxidizes completely to COH. So benzoic acid is going to be the answer. Is it clear?
Yes, sir.
Yeah, okay. The other reaction is acetylation. What do you understand by acetylation reaction? Just you can tell me quickly.
Adding of an acetyl group.
Yeah, adding of acetyl group. And acetylation occurs on which two functional groups?
Carboxylic acid.
No, not carboxylic acid, on alcohols and amines. Okay. And what are acetylating agents? So you remove HCl, okay, and this COCH3 group attached to the position where H is there right now. And you remove HCl, and in this you remove acetic acid and you put in the COCH3 group in place of H. So you are going to end up with ROH is going to change to ester with an acetyl group. Is it clear?
Yes, sir.
And so what's the common use of acetylation? Preparation of aspirin. So how do you prepare aspirin? Yeah. How do you prepare aspirin from phenol? Suppose if someone asks you, then what you are going to answer? Aspirin, how you are going to prepare? So phenol you take, Hanifa, and phenol you convert it to salicylic acid either by taking CCl4 or NaOH, or by taking NaOH and CO2, right? So you are going to end up with carboxylic acid group at the ortho position. Then you take acetyl group. So HCl is going to remove, and you will have acetylated salicylic acid, which is known as aspirin. In your school viva also, they will ask, this is so common. So what's the IUPAC name of the aspirin?
Acetyl salicylic acid.
Not acetyl. Yeah, acetyl salicylic acid. Okay. Yeah, IUPAC name. That's the common name. So 2 as this is the principal functional group, okay, and this is benzoic acid. So 2 on the second question you have acetoxy group, okay, 2 acetoxy benzoic acid. Is it clear?
Yes, sir.
So
So can you again repeat that name, IPC name?
2 acetoxy or if you want to become more formal, then it is going to be 2 acetoxy benzene carboxylic acid, right?
Yes, sir. So then what is this like aspirin and acetyl salicylic acid is the common name. Then this aspirin, what is it?
Name used by the doctors as a medicine. This is used as an antipyretic drug or painkiller and fever also, right? Is that clear?
Yes, sir.
Aspirin, antipyretic drug. Hanifa, is it clear? Now
Yes,
the
sir.
next thing is okay, good. So now next thing is reaction with active metals. And alcohols have active hydrogen, acidic hydrogen, and the moment you're going to put sodium and all, what is going to happen? The sodium is going to liberate the hydrogen gas, right? And this can be used to identify alcohol from different functional groups, okay? But selected, it can work only on selected groups of functional group for the identification, okay? For example, if I give you one formula C2H6O, right? And if I ask you, it has two isomer X and Y. X upon putting sodium liberates hydrogen gas, and Y upon putting sodium doesn't liberate H2 gas. No H2 gas is liberated. So what is X and what is Y? Is it clear? This can come in your board examination also. It's so important.
Sir, can you please repeat?
Pardon?
Sir, can you please repeat?
Yeah, X and Y have same formula C2H6O. And if you put piece of sodium in X, it liberates hydrogen gas. And Hanifa, if you put sodium in Y, it doesn't liberate hydrogen gas. Okay, X and Y, they have same formula C2H6O. X liberates so hydrogen gas. On the other hand, Y doesn't liberate hydrogen gas. So what is X and Y? Tell me. Very important, very basic. Yeah, Hanifa and Samara, quickly tell me.
The sodium alkoxide.
No, yeah, sodium alkoxide, where?
In
Where?
X, X will
In
be.
X is which functional group? X is ethanol. Okay.
Yeah. So sodium, no, ethanol.
Yeah, no, sodium ethoxide is going to form after the liberation of H2. I'm not asking what you will get after H2. I'm asking about the original compound before putting the sodium.
Yeah.
What is X and what is Y? So X is ethanol and Y? What is Y? Definitely Y is not ethanol because it's not liberating H2 gas. So what is Y?
Methanol.
No, they have same formula. They are isomers. Okay, that is ether.
Oh, okay.
Is it clear?
Yes.
So ether, because so this test is a very basic test, but it can work only for distinguishing alcohol and ether. But you can't distinguish alcohol and carboxylic acid because both have acidic hydrogen. Right?
Yes.
Clear? So very, very important. Similarly, this phenol also is going to liberate hydrogen, and this you need to know. If you have same formula as that of alcohol, but it is not liberating hydrogen, means it is an ether. Clear?
Yes, sir.
Now the next reaction is acid catalyzed dehydration of alcohol. So just general we can discuss. There are more details. Just a few things we can discuss. Very important. So you take alcohol, you heat it with the concentrated acid. Which concentrated acid you take? H2SO4 or H3PO4. You heat them, and you end up with what? Yeah,
Alkene.
alkene. Yeah, it is removal of water, H and OH from adjacent carbon atoms. You end up with an alkene by the removal of water. So that's why it is called dehydration, means removal of water. Okay. And this is an elimination reaction. What type of reaction? Elimination reaction. Okay, suppose this is not a redox reaction. This is elimination reaction because two groups are removed, and you require heating. Okay, so for ethanol, the more and more branching is there on the alcohol, the more ease will be observed for the removal of water. The water will be removed more easily. Okay, so suppose you can see ethanol, isopropyl alcohol, and tertiary ethanol. Tertiary ethanol actually just by little bit warming it can undergo elimination reaction and it is going to give you an alkene, right?
Yes.
So that's how it works. Uh, though there are more details, it's a mechanism and all that we can cover up in detail. Okay, so just today we can just discuss about little bit about ethanol. So in ethanol, what are the temperatures? Can you tell me at which this elimination occurs in degrees Celsius? Yeah, So it's 170 degrees. And if you take conc H2SO4, then also water will get removed, but not from one molecule, but from two molecules, and you will end up with an ether. Clear? And if you take lesser temperature, so you need to remember this. This is very, very important. And it is there in your NCERT also.